Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Konrad.
Welcome, or hopefully, welcome back to the Reliability Matters podcast. For those of you who are counting, this is episode number 136. We covered the topic of ultrathin conformal coatings back in November. We covered various conformal coating materials from traditional acrylics and silicones to ultrathin parylene coatings. But what other coating materials are available? Where do these coatings fit within the specific applications? Where do health and safety, environmental concerns, and sustainability programs fit with a coating process? To answer these and other questions, I invited Dr. Cassandra Zentner, Vice President of Health and Environment at Actnano, a manufacturer of conformal coating materials, onto the program. Cassandra earned her BA from Oberlin College and a Ph.D. in Organic Materials Chemistry from MIT. And today, she's been promoted up to Reliability Matters podcast guest. It's my pleasure to welcome Dr. Cassandra Zentner to the program. Cassandra, thanks for being my guest today. Congratulations on your promotion to podcast guest.
Yes, it's I think the biggest promotion of my life so far. In my career,
yes, and I've got the honor of sitting next to you virtually anyway. So, no, thanks for being here. I didn't preview this with this question because I always like it to be a little bit of a surprise. But tell me and your audience and those who know you something about yourself that maybe people wouldn't have known otherwise. There's a hot seat question for you.
Yeah, because I think I'm a pretty open book. So trying to think.
So you have to dig deep now. Huh?
I do, because you included like friends and people who know me, so what they don't know about.
Well, let's take maybe 3 degrees of separation.
Okay, so we can do that. So I am actually a first generation Irish American, and the majority of my family is still in Ireland. So that's a big part of my life, and kind of also how I approach work and family. There's a lot of influences there.
Well, that's why I like you so much. I am first-generation American as well, and my parents came from Scotland. So just this far away from where your family grew up.
A little bit.
Yeah. I assume you go back to Ireland from time to time?
I do. I'm usually there a couple times a year since a lot of the family is still there, and we have our home place there and everything.
Yeah. I do too. My wife is Scottish. I was married in Scotland 43,000 years ago. And so we go back and forth a couple times a year. My wife usually a few times a year. And that's the deal I made when I went over there as a 19-year-old marrying this 18-year-old Scottish lassie. I said, and it was a total hollow promise because I had no means to fulfill my promise. But I said, if you marry me, we'll live in California, and you can go back as often as you want. In the early days, that was quite a promise to make because we didn't have any money. But we managed to get there. It worked out, and her family's all still there. So, I do like that culture, the whole atmosphere in Ireland too. I think the Irish and the Scottish are very close in culture, and
certainly some overlaps there.
Yeah, slight tweaks with the accent. I do think the Scottish accent, particularly on the West Coast in Ayrshire, is probably the most difficult accent, even harder than a hard Irish accent.
I would definitely agree. I personally had a lot of issues when I was in Scotland trying to get every part of the Scottish dialect also, because there are some interesting Scots words that can kind of fit in. And I think that complicates a little bit more. At least for Ireland, I know the dialect, I know the slang, so it's a little bit easier for me.
Yeah, when I would go over there with my American friends, in fact, we were just there about a month ago, and my wife and I were the official tour guides for our 10 American friends who wanted us to show them around. At one point, one of them thought that we were punking them because they were with my family, and they looked at me and they went, "They're not speaking English. They're just making this stuff up. You're just You're just trying to punk us. And we're like, nope, this is real. This is real. Now, how do you understand that stuff? It's how I grew up with it. Yeah, it's one of those things you just have to immerse yourself in. So,
very true.
As much as I would love talking about Celtic culture for the whole day, let's switch to the second most interesting topic in the world, which is conformal coating. I've done a few episodes on conformal coating, including one just back in November. But every time I do it, I get a slightly different outcome. You know, there's nuances and there's opinions and there's just different ways to look at it. So even though I've asked this question before, I think every time I ask it, I do get a slightly different answer. So can you explain the primary types of conformal coating materials and their properties? We'll start with that. That answer will probably be pretty uniform, but then we'll probably stray off the track at some point.
Yeah, so in terms of conformal coatings, there's a few different ways to think about it, but how most people approach it is the thicknesses that you achieve and the types of chemistries that you have. So you mentioned ultrathin for one of the conversations that you had back in November, and that's something that lower than 12.5 microns is considered an ultrathin coating. Doesn't matter the type of chemistry, it's ultrathin. But then you get into all the different types of chemistries. There's silicones, polyurethanes, acrylates, acrylics, epoxies. I'm sure I'm missing some. And these are in, say, the category of a little bit thicker. So you're 25, you're 50 microns or higher until you get to, say, potting level. So those are your two big categories. You have thickness-based, you have chemistry-based, in the way that most people think about it. We think about it a little bit differently. Because we're an innovative company, and one of the things that you'll hear me say a lot is traditional conformal coating versus Actnano's conformal coating, because we make an even bigger distinction there as well, in the sense that traditional conformal coatings are hard barrier. So if you were to touch them, they are hard, whereas ours are a softer material. And that kind of puts us in a little bit of a different class that currently is not characterized by any of the standards in the industry.
Let me ask you then, if it's a softer material, does that translate to being more pliable to a certain degree? Or
I wouldn't say pliable.
Okay.
It's not like you aren't going to be able to, say, grab the material as if it was an elastic band and pull it and come back like that. It's more of thinking, say, something, although this is definitely more deformable, like Vaseline. So something that you spread across and you could imagine like moving that. So it's more like a soft material in that sense than it is in an elastic sense.
Okay. All right. What, of all the different types, what are the driving factors that should be considered when choosing a type of conformal coating? An acrylic all the way to a parylene to something in between. What types of either application factors or voltage or harsh environment, whatever. What goes into the mix to come up with a preferred material?
I'd say there's three different things that go into it. The first is just your reliability requirements. So what is the board expected to protect against? Is it expected to protect just against water? Or are there harsher conditions, corrosive gases, or any sort of salt conditions? So that's one. How strict are the reliability requirements? The second is the board itself. What is the makeup of the board? What is the geometry? What is the voltage? Because that can have a major impact on the type of material and the thickness of material that you need to do. And then the third is really at the factory level. And this, I think, is one that people kind of forget or devalue a lot, but is actually one of the most important things to consider, is that the factory is where you're applying it. What materials you need or what equipment you need to be able to apply it, in addition to what equipment they already have. What are their health and safety requirements that they have in place? How do you handle the material? There's a lot of different considerations at the factory level that tend to be downplayed, I think, when people are looking at just reliability requirements.
Yeah, very good. We talked when I asked you if a softer material was more pliable, and it wasn't. That was a good example of what it's not. A silly putty kind of stretchy thing. Right. How are conformal coatings applied to maybe flex circuits, something that may move around a little bit in, maybe a wearable or something like that. I would think that the need for conformal coating on a wearable device is probably greater because people wear things outside, and sometimes it's a harsh environment outside. So how is that handled? I would imagine if you have a super hard material, maybe like an acrylic. I'm not sure. I think acrylic would seem to me, as a layman, to be less pliable than a silicone, for example.
Yes, that's true.
If I were to take a circuit and just bend it just a few degrees, it could crack the conformal coating, even though the laminate material, or the material that it was built on, is flexible, but maybe the coating is not. How is that handled?
Well, I think that the idea of flexible circuits, there's two ways you actually really see it. One is what you're describing, say where you have a printed circuit that is actually flexible itself and you'd be able to move the circuit. And there you would be hard pressed to use a traditional conformal coating, depending on the degree that you're bending it. Okay? As you say, like as you bend it, you're going to get resistance and potentially cracking with these harder barrier coatings, or it's just not going to let you do it and get to the level of functionality that you need. And this is where a soft barrier coating, so these gel state coatings that Actnano specializes in, can be helpful because although they're not pliable in the sense of an elastic band, you can bend them without damaging the coating. But a lot of the flex circuits that we see is a bit of an anomaly in the sense that their circuit themselves is not flexible. It's on, say, a flexible ribbon that the PCBA or the connector is not flexible itself. And there it's the same considerations as a typical PCBA or other electronic component that you're looking to protect as to whether you use a traditional conformal coating or an alternative.
I would think also that if the circuit was, or the substrate was being flexed in use, obviously the components, we haven't made a flexible QFN, or a flexible BGA.
Right.
So I would imagine if there was a requirement to protect the components, one could spot conformal coat, maybe not with every type of material, but one can mask off certain areas so that would allow the substrate to be flexible and still protect the component. Is that an option in that, if that was the strange requirement?
Yeah, you do see selective coating, and this is possible across a variety of different types of coating chemistries, coating thicknesses, whether it's a hard barrier or a soft barrier. There, you're thinking of just like one particular area that you're protecting, and that is definitely possible, and we do see that in different applications. The key there is that if you're only protecting one particular component, there's a lot of the board or flex circuit that is not actually protected. So you are liable for corrosion or other things to creep in because only some part of it is protected.
Sure. Yeah. I guess it's all a matter of compromise at that point.
Yes.
So let's just review for my audience's sake and mine. I blame my audience, but it's really me who wants to know. Let's go over the various methods that conformal coating material is applied. I know there's spray, there's vacuum deposition. I don't know if there's alternatives to that. But just kind of walk me through the process of the various materials and how they are applied.
Sure. So when we think ultrathins, that's where you have, say, your vapor deposition, whether physical or chemical vapor dep. And you also potentially have dip coating. So that is one way to apply conformal coatings, is through dip coating or those vapor deposition methods. But when you get into the coatings that are thicker, so, the silicones, the acrylates, the polyurethanes that are, say, the 25 microns or higher, you start using different equipment. Dip coating is still possible. That's something that you'll see across a wide range. It just tends to give you thinner coating. Atomized spray is one of our preferred methods because it can coat a large part of a board or a very large surface quickly, so it reduces your cycle time. But there's needle dispense, which you can do from an automated machine. There's also jetting. So this is small dots that you're placing on the board. And that's where you think about selective coating or only one little area. Jetting is maybe a preferred method for that. And then you also have a film valve, which is less used, I would say, but it's basically a very wet application of your material in like a film that goes across the board. So those are your automated ways, but you'll see manual ways as well. I've seen places that have wanted to do manual hand spraying, which I would argue is probably not that reproducible. The technicians might argue back with me on that, but that is one way that we've seen conformal coating applied, manual needle dispense, and then also what's called brush application, which is literally like a paintbrush that you're kind of going over different components. So there's a lot of ways.
Yeah. I would think that the technicians who would argue about reproducible are arguing in the abstract. Their material, their application might be reproducible, not necessarily compared to the person next to them, right? It's kind of the weakest link syndrome. So one of my favorite subjects is environmental responsibility. I own a manufacturing company. We build cleaning equipment, and several years ago, we made a commitment to be zero discharge. So not a drop of fluid goes to drain. And that was quite radical because the technology's always been there to do that, but no one really embraced it because they thought, oh, well, it's too expensive to do it that way. No one will buy it. And then when we actually ran the numbers, we realized that it was a little bit more expensive, marginally. But then we factored in what's the cost of liability? What's the cost of getting caught putting something bad down the drain? What are the net cost increases or savings? And I would argue it's definitely a savings. But people do pursue quote unquote green. They pursue two greens. Some pursue the green like save the planet, do the right thing for the planet, make the world a better place, et cetera, et cetera. And some are a little bit more savvy. They count the numbers and they go, no, it's cheaper to be green. And the green they're chasing is the cash, right? But either way, good results. I've been into several contract coating houses because we sell cleaners, so sometimes we sell cleaners to those people. And without exception, every time I go in, the smell is overtaking. I don't think they can even smell it anymore. I think they probably have no sense of smell anymore, or they're just so used to it. But to me, it was almost like walking into like a nail salon. That solvent smell that you have. Only it was worse. And I saw all these stations with vent hoods, and I saw people wearing personal respirators. I just kept thinking, this can't be good. This can't be good. Talk to me about. I know your involvement with Actnano is on the environmental sustainability side. Which prior to hearing that almost seemed like an oxymoron, conformal coating and environmental responsibility. Not that it's a dirty business, but it involves chemicals, which in order to do their job have to be fairly strong chemicals. So tell me how those two subjects kind of merged and your company's stance on sustainability and environmental protection and things like that. There was a quote on your website. Let me see if I can find it. Our focus to provide effective coating solutions that are both human safe and environmentally friendly has enabled us to create surface protection technologies without the hidden dangers, such as toxic PFAS or I love this phrase, toxic forever chemicals. So how have you detoxified? I know that's probably not a technical term. I don't think anyone would recommend drinking the materials that you make or anyone makes. But so when I say detoxify, I'm just using that as a relative comparison. Tell me about your company's pursuit of environmental friendliness or responsibility, sustainability, and less toxic chemicals came about.
Yeah, and I could probably spend an entire hour talking about this, so I'll try and keep it to the high level.
This will be a
points.
5-part. We'll do a 5-part. We'll just do like a monthly a talk with Cassandra.
On sustainability. Yeah, I think the big part for us is the idea of using safer chemicals. So you mentioned kind of walking into a factory, that strong smell, you are instantly feel like you're enveloped with chemicals. And this is actually something that our CEO, Tamar Ahmad, noticed in his previous role, where he was actually running global factories for his previous company. And when he stepped into the factory, he actually saw from a worker's perspective that they seemed to be prematurely aging. They weren't able to breathe very well. And a lot of this was coming down to the chemicals that were being used in, say, the coating materials. If you've ever heard of isocyanates, that is an example of a toxic material that can be found in conformal coatings that is a respiratory sensitizer. So the more you are around it, the more your body becomes sensitized to it. And once you get to a certain level, you're not able to really breathe. It gives you these very strong asthmatic responses. So he saw that, and what he wanted to do was develop a company that not only gave better options to the electronics industry from a protection standpoint and performance standpoint, but also to bring products that were human safe. So it's been part of us from the very beginning, but you can say that, but how does it actually look in practice? So for us in practice, it really comes down to our product development stage. We use materials that when it's applied on the board is going to be non-toxic to the best of our knowledge and kind of say academic and industrial knowledge of the materials that we use. So if you were to handle a board that had Actnano's coatings on it, any of Actnano's coatings, you can handle that without gloves. You can touch that. It's not going to cause you any harm. And the bonus is that it's not like these forever chemicals that'll cause harm to the environment over time as well. So this was part of our very beginning, and we haven't strayed from that over the 10 plus years that the company has been in business. So it really what you are feeling when you go into a factory, it may not be the solvent because that can be captured by ventilation systems. It is actually maybe down to the chemicals that are needed for the curing process or off gas during the curing process for many traditional conformal coatings. And that's hard to, say, capture in the same way. So that's where you see a lot of those issues. So, go ahead.
In the consumer world, let's look at food. If something is sold as low calorie or gluten-free, there's a cost on the other side, like it doesn't taste good, right? We all like the stuff that's bad for us. Is there a little bit of a trade-off to go less toxic chemicals as opposed to more toxic chemicals in terms of function and performance? Is there a trade-off at all on that?
Not from our experience, but I'll caveat that by saying that going down this route is the harder route.
Yes.
We have very innovative people who have thought about this and have developed chemistries that are able to match, say, the toxic chemistries of other conformal coatings. But it's not easy. It's kind of doing the hard thing to do the right thing, I guess is the way to think about it. And a really good example of that is PFAS. You were saying is on our website, PFAS. This is becoming a household name, particularly in those of us that are connected to chemicals. It's per and polyfluoroalkyl substances is what that stands for. And you'll see articles that come out about PFAS being found in water, forever chemicals being found in water. These are extremely toxic. But the reason that they were used is because they're very hydrophobic, so they repel water really well, and they're very stain resistant, so they repel oils really well. So the industry, not just conformal coatings, but broader electronics industry, consumer devices, consumer clothing, textiles, used a lot of these very toxic materials and are only now trying to phase them out. And it's a hard problem because they're so good at what they do, and that's why people use them. But that's where innovators like the people that I work with are important because they know they're not going to use those and they're going to develop to match those. And we've been able to do that.
Yeah, excellent. If it's low calorie, it doesn't taste good. But you've broken that trend a little bit. It sounds like it's
yes.
if you were in the food business, it would be low calorie, gluten free, and still taste yummy. So
exactly.
Good for you. You talked about it earlier when you were describing the various conformal coating materials that there are quote unquote thicker materials and thinner materials, all the way down to nano coating type materials. Is there a difference in the level of protection based on the thickness of the material? Obviously you can go as thick as potting, or you can go as ultra thin, kind of nano coating, and then there's areas in between. Are there links between protection and thickness or are they unrelated?
Not necessarily connection. It really depends. So within a, say, coating type, if I have an Actnano coating, if I increase the thickness, it's going to, up until a certain point, increase the overall protection level. And it's a lever we can play with when we're trying to customize solutions for particular customers in harsh environments. But if I were to say compare Actnano's coating to parylene, which is ultrathin, to a traditional conformal coating, say that is UV cured, that's thicker, you don't have that same correlation. It doesn't mean that parylene protects less well because it's the thinnest. It really is within a material type that you can kind of make that correlation.
Yeah. Okay. Very good. What are some of the key challenges when applying conformal coating to a printed circuit board? I'll throw out one because it's in my best interest to do so. From a purely selfish standpoint, cleanliness of the substrate, whether you're painting a car or a wall or applying a coating or plating a piece of metal, cleanliness is always important. I've seen lots of instances of delamination, and that's usually because it wasn't good surface preparation. Do you agree with that statement that it should be clean?
Yes.
Okay, good.
I'll add a caveat. I would say traditional conformal coatings, very important because they have a tendency to de-wet or not wet across the surface. So that's the ability to spread across the surface.
To be conformal, right? Otherwise, you don't have the conformal in the coating. Yeah.
Exactly. So that is a important factor. So even when you think about no clean flux materials, they're not really no clean for every single type of coating material. The reason I would put the caveat in there is because Actnano's coatings are applied in a slightly different way. They have different say chemical properties. So we haven't seen that same issue. It's one of the things from a value proposition that we bring to our customers. But when we're thinking about the overall conformal coating space and the way most people think about it and most materials that you work with, cleaning is an important step that the industry is kind of industry standard.
Yeah, one of the things that I think a lot of assemblers don't consider is they're fairly convinced, and accurately so, that the residues left behind from a no clean flux species are fairly benign and invisible and not really all that problematic. What they don't take into consideration is if they choose not to remove the flux, they're not removing anything else either. And I always thought that it was a bad idea to call a defluxing process because it's not just defluxing, it's definger oiling, it's mold release agent, it's hassle finish contamination. It's all the sins of the process all along the way, all pile up, and then they put flux on top. And then if we're told the flux is cool to stay on, then we just kind of let everything else go. So I really think instead of calling it a defluxing process, we need to really call it a cleaning process. And whether or not it needs it is to be determined. But beyond having the appropriate surface energy, the appropriate level of cleanliness for good adhesion, what are some of the other challenges that certain types of assembly designs present to conformal coating applications?
So when we think about purely the application space, so how does the material apply on the board? A lot of this for traditional conformal coatings comes down to their viscosity. They tend to be higher viscosity materials, so not like honey, but also more viscous than olive oil. You're kind of in an in-between space there. And one of the issues with that is it can trap air really easily. And what you'll get on the board are bubbles. So you get defects, pinholes, other items like that because air gets trapped into the material as it's being coated onto the board. So that introduces some defects. Another issue is the actual flow of the material. So if you have a viscous material, you're applying it, say, needle dispense. And as this goes across the board, sometimes you don't get even spreading. This can come down to say how clean is the board. That is one component, but it's also down to the material itself. So different things can happen. You get kind of this ripple effect that's called orange peel. and that is due to the non-uniform spreading. And the last one I'll mention, which can come up in two ways, is cracking. So cracking, when it's applied, tends to come from the fact that maybe one area is not curing at the same speed as another area, or the coating is applied thicker in one area than another, and you get those issues, and as it cures, you get cracking. So that can come up with these kind of viscous materials and curable processes. And cracking also can come into play when we talk about reliability testing. But if we're thinking about pure application, it tends to be at the curing process. So these are issues that come up for materials that are lower viscosity. So our materials are lower viscosity. You also see some kind of thinner conformal coatings be lower viscosity. They don't have those same problems. They can apply more uniformly. They can apply without trapped air, and aren't going to see the same cracking problems. But it really depends kind of on that viscosity and chemistry makeup of the material.
You talk about curing. Obviously, that's an important factor. How does the choice of curing methods like UV or thermal or chemical, whatever magic formulas you have, how do those curing methods affect the conformal coating process? And is there a particular curing method that you think is better in terms of consistency and thorough curing than maybe others?
Yeah, I would say the no curing method is probably your best bet, because at the top of the line, curing versus no curing is going to be your biggest impact. And a lot of that comes down to the factory level. If you don't have curing ovens of any type, then you aren't going to take up floor space with ovens, which is very important in many factories of getting as many lines in as possible. And you save on the energy costs and the environmental impact by reducing energy costs of running ovens. So that's one thing, is like if you don't have a material that needs to cure, you already have an advantage from that standpoint. So there are materials like Actnano, we're not the only ones, that have a no cure process. So through solvent evaporation in the coating machine itself, when it comes out, it's good to go. Right? There's no curing.
So would a better term then for a no cure process be just drying? It just has to dry?
Yeah.
Like paint doesn't cure, it dries, right? So it's kind of
exactly
analogous to that? Okay.
It's the same idea. Yeah.
So curing is a accelerated process, right? It's kind of a cheat a little bit. I don't mean it's cheating, but it's a UV is like almost instant curing, right? So and thermal is a more rapid, maybe less rapid than UV, but a rapid curing as opposed to letting it dry. Is there a time difference involved?
Yeah, it really depends on the system. So say for our materials, they are basically dry when they come out of the coating machine. So within 10 to 30 seconds, they're dry. So we are faster than most curing systems, but that's not true of every evaporative process or ambient cure process where you don't need heat. Those tend to take 24 hours if you're just letting something sit out and it's doing ambient cure.
Right. That's when you don't want the fly to land on the board while it's drying.
You have special storage to let it dry. Yeah. So those are two different types of drying. Ours say is quicker, and there are materials like ours that can dry relatively quickly. When it comes to actual curing, UV ovens tend to be the most common one that you see, and it's because exactly what you said. UV is one of the quickest ways to cure. It's one of the most well-known kind of initiation ways to cross-link and cure a material. So it's very common. Factories tend to have UV ovens. So when we see something, it's usually UV, but you do see thermal ovens. They're a little bit slower, also very energy intensive. You have infrared, so IR ovens that sometimes can come up. So they are vary in their speed at which they cure. But from my perspective, you should get rid of the ovens, just even from an environmental perspective. They take so much energy that if you don't have them, you're already making a good impact.
A different application of UV, one is for curing and one is for tracing, right? So you can tint the material so that it can be inspected under UV light to monitor its coverage, to inspect for coverage. Do you think that's a good idea to do that? Does that have a downside? Does it affect the conformal coating in any way other than allowing it to be viewed more easily?
I would say 99% of your materials are going to have a UV tracer in them.
Okay.
So there isn't, and because almost every factory requires automated optical inspection, so AOI, of the board after coating, or a manual inspection. And really the only way to see if you coated where you were supposed to is through those UV tracers. So there's not really a downside. They don't, at least from my perspective and my chemical understanding, you are not going to impact the performance, the lifetime, or any other of these concerns by adding a UV tracer. And it's an important part of quality control at the factory.
What you mentioned, orange peeling, maybe delamination. What are some of the other common and maybe even less common defects that can occur if conformal coating, either the inappropriate material was chosen or the application didn't match the material, climactic induced environment or exposure to harmful things, or the process wasn't applied, the material wasn't applied properly. What are some of the poster child defects that can occur? We'll call it, stupid people tricks. When things go wrong, what are those things?
Yeah, and I think this is where your UV tracer is going to give you a very clear idea. So if you are outside of inherent issues with the application that we've already talked about, where you get pinhole defects or you have air bubbles, these are all things that can happen and people try and mitigate at the factory level. But sometimes, no matter how you apply, you're not going to get rid of defects. And a lot of that comes down to the increasing complexity and the geometries of a board. So when you apply conformal coating, one of the challenges is that you might have very low height standoffs for some of the materials, and you might have very large capacitors on the board that are pretty high comparatively. These complex geometries make coating more and more difficult as boards become more and more complicated. So you start to see defects where those larger components aren't actually coated. Material has flowed off of them. Maybe the corners aren't coated, so you're not really getting that full protection. And that's becoming more and more common, I would say, with using traditional conformal coatings. You can mitigate this with using something that is low viscosity from an atomized spray, is that application technique is going to give you better coverage overall on these complex geometries. Or you can use angled valves, which are also something that is becoming more common to at least have that capability in coating machines to be able to kind of coat some of those complex geometries. But it's one that people don't typically think of. But now we see more and more as boards get complex that application of materials becomes more and more complex as well.
Conformal coatings have been known to discolor a little bit over time in the field. If someone's coating over, say, LEDs or some other type of illumination that requires a certain color to be broadcast or a lumen value, intensity value, what are there certain coatings that discolor less? Do they all discolor? Do some never discolor? What would a thinner coating be more appropriate over a thicker coating? These are just kind of the logical questions that come to mind. How do we mitigate that?
Yeah, so you'll actually see a lot of customers coat or mask LEDs for this reason, with a lot of traditional conformal coatings that are, say, optically clear or relatively optically clear to start. Through UV exposure, through, say, that LED or just general exposure to ambient light, they discolor. So they degrade a little bit over time. Or this is where the UV tracer could potentially be a issue, is if you have the UV tracer, sometimes they can discolor. And this really only is an issue if it is, say, on an LED or some optical device. And it really comes down to the chemistries. I couldn't tell you, say, one silicone over a poly acrylate or a polyurethane that they would be one better than the other. But if you were choosing something to coat over an LED, that's something that you need to know from the supplier is, one, are you optically clear to start? Do you cause any sort of shift in color just from coating, which many do, or does it degrade over time? So showing, say, after 1,000 hours of exposure to this particular type of light, what happens? But I don't have a good answer for you in terms of which chemistry or which products should you go to for that. It's just some considerations you should keep in mind.
Are your products specifically applied through one method, like vacuum deposition or spray, or do you have a variety of application methods for your company's specific products?
Yeah, so for our company-specific projects, we definitely do not do vapor deposition. That's a different type of chemistry. That's a different type of material, and one that we want to.
That's more parylene. Is that more?
That's parylene.
Okay.
Yeah, that's parylene, and it's specialized equipment. It definitely has its space that it is really the winner when it comes to the type of material to choose. But I would say generally, vapor deposition is not something that we do, and for many reasons in terms of what we think is the best and most implementable technology. For our materials, we tend to use spray the most often. Because our material is low viscosity, we're able to spray really quickly. This gives you quick cycle times, quick drying times at 10 to 30 seconds, and then it can be assembled. But we do also do dip coating of some of our products. This is something we're expanding into, particularly in replacing those PFAS coatings. Your 3M Novec coatings that are no longer going to be on the market. They're dip coated. So we are developing and working with customers on dip coating. And the final way we tend to apply is through needle dispense, but this isn't a very unique way. So typically, conformal coatings, you want to avoid them getting underneath components. And this is because during reliability testing, particularly thermal exposure, they can actually pop off BGAs or cause mechanical damage to different components. So you want to avoid needle dispensing and going around components that are raised off the board. For our coatings, because of that unique soft gel state nature, we actually bring value by going underneath components and protecting them underneath, and we don't have those same problems. So that's why I say needle dispense, yes, but it tends to be for this kind of unique 100% protection of different components on the board.
So do your coatings just not affect heat dissipation, or do they enhance heat dissipation? Is there a thermal characteristic with your coatings?
So there's two different types of thermal effects here. The one I was mentioning where we can coat underneath components and we're not affected by, say, the thermal shock, the thermal variations, is more down to, say, the when you hear coefficient of expansion. Right? So for a lot of conformal coatings and, say, the solder balls underneath BGAs, they vary so much in their coefficient of thermal expansion. When you go through these rapid temperature differences, that causes stress because they expand, contract at different rates and to different extents. And that's where you get, say, pop-off and mechanical failure of those raised components. Our material is applied underneath and in thinner, so we don't fill that full void space, and we're that kind of soft gel state material. And this basically means we don't have to worry about that mismatch. It kind of flows with the changes in the solder balls as they go through the thermal shock. So that's one type of thermal effect that you need to keep in mind. The other, which is, I guess, not particularly related to kind of coating underneath components, but is important for electronic devices, is thermal dissipation, right? How thermally neutral is your material? And this becomes important when you're thinking about ICs, say when you're coating over ICs and there's a heat sink that tends to come in contact with the IC through usually some thermal paste. It has a high thermal conductivity. So most conformal coatings and Actnano's materials included have a very low thermal conductivity. So this means that they're thermally insulating, and you wouldn't normally get that thermal dissipation through the coating. So that would be a major problem and why people mask these areas.
Right.
Our coating and like ultrathins that even if they have, say, low thermal conductivity, because they're thin and you can deform our coating, that's kind of when we say soft material, gel state, one of the things is it deforms. So if you apply pressure, it thins out. And what that can do is it actually makes the coating thin enough that you can get thermal dissipation through it. So that's an important distinction, is that it's not only the material thermal conductivity, it is also the thickness of which it's applied.
You talked about masking for a variety of reasons. Is there a particular method that's just uniform on how certain maybe components or areas of the board are masked? Are there variations? Are there different ways, varieties of ways to mask? And if so, or is there a preferred masking method from your standpoint?
I think we're going to have the same answer as we had for the ovens.
Wait a minute.
The preferred method is not to mask.
Right. Oh,
No,
I see what you're saying.
Preferred method is not to mask. Yeah.
I thought you were going to throw in "it depends" on me, because that's a
No,
common answer in this whole podcast, Reliability Matters podcast. Is a lot of the answers are "it depends," which is really a good answer. Yeah. But gives you a lot of cover. But okay, so you would prefer not to mask.
Prefer not to mask, which we can tackle that in a second. But from your question in terms of when people do need to mask, there are a variety of methods that are used at the factory level. One of the first methods is just tape. So you use tape. This is a manual application. You cover the components or the solder joint or anything else that you need to mask and protect. And that's one of the ways. And then you remove the tape after coating. You also see kind of gels or pastes that are used with a similar idea. You apply it to the particular component or area and you remove it after coating. These are not reusable. It's a very manual process, but they are very common. Things that are maybe a little bit more reusable, and it depends on the material that you have, is that people can use caps. So say little plastic caps that can go on different components. I would say we've never really encountered that in a factory of anybody who does that, but it is an option. And the final way that we've encountered is actually through fixtures. So say you only have a small part of the board that needs to be masked or kind of looking at a particular area. Sometimes people will make fixtures that can just go over each board. You spray whatever you need to do, and then you move on. That can become difficult if your material is hard to clean, because you can only use the mask so long before you've built up enough material that it is no longer useful. But it is something that you can see in factories as well. So those are the typical methods. But the thing that to keep in mind for masking is it's very labor intensive. If you need to use tape or gels to be able to mask, it is manual. It is typically a manual process. It takes a lot of time. And when you are doing the conformal coating, that's where most of the labor is in the whole entire process. And most of the time is in masking. So that's where no masking is really the area you want to go. It's just not possible with every type of material.
So we talked about the application of conformal coating, how to put it on various different methods, vacuum deposition, sprays, and dips and things like that. Let's talk about how to take it off. There are times when a component has to be changed out. There needs to be some rework, and that's always been kind of the fly in the ointment when it comes to conformal coating, because it's designed not to come off. It's not supposed to be easily removed, right? That's the whole idea. For your types of materials, what would be the preferred or recommended method to rework and to remove either all or a section of conformal coating? And then what do you recommend someone does after the fact?
Yeah, so every OEM says that rework doesn't happen, right? Because they don't want to believe that rework happens. And I think everybody who's worked in a factory knows that rework happens.
Well, let's say hypothetically, if we need to rework something. Hypothetically.
If you needed to, in that hypothetical situation that we have never encountered, you do see with a lot of traditional conformal coatings exactly what you said. They are hard barrier coatings. They are meant to not come off of the board, and they tend to take high, say, thermal requirements to be removed or very harsh chemicals to be removed. So this is something that is a daunting task with many coatings. For our coatings, they actually are very easily removed with solvents because we sell mostly solvent-borne coatings. Those same solvents can help remove it. So this is something that is relatively straightforward for our coating, but is difficult, as you mentioned, for many traditional conformal So the process is just you take a swab, you clean off the coating with some solvent, you rework the material, and you're able to use manual application of the coating material after the component has been reworked.
So you don't need to, there's not really a recommendation to use a abrasive material, kind of a sandblasting, if you will, material. There are other types of conformal coating materials where they're not so easily solvent dissolved, right? So they have to be put into a abrasive chamber, and sprayed and manually, usually with someone with gloves inside this cabinet that is spraying it. That's not necessary with your type of products.
Not with our type of product, but yeah, those kind of high abrasion scenarios or high heat, so say thermal decomposition of a particular material are the harsher ways to go about it. It's not necessary for us, but it is necessary for other conformal coatings.
How do we evaluate the long-term reliability of conformal coatings in different environments? What are some of the maybe more challenging environments that your customers see, and how would one evaluate, based on those perceived challenging requirements, what type of specific type of material, specific type of thickness that, how does someone kind of calculate that in advance based upon your company's experience?
Yeah, so I would say the core of our company was originally in automotive. So many of our initial customers were in automotive, and most automotive companies have very strict reliability guidelines and standards. And within these, every coating has to pass a certain set of tests to say that they reach the 10, 15-year warranty and lifetime that's expected in a vehicle. So the types of tests that automotive typically tests for, one is thermal shock. So we talked about this a little bit, where when you go through those temperature variations, you can cause mechanical failures on the board due to the thermal coefficient of expansion issues, but you can also cause cracking in coatings when, say, there is flux underneath or contamination that has that same problem, and you get the coating itself cracks. So thermal shock is one of the harsher tests and is very common in automotive and in some consumer devices if they really want to hit at like a very thermally difficult test. But that's the standard, but you start seeing more and more harsher conditions. So salt fog, salt mist, salt spray, these are all highly corrosive environments that you also see in automotive and in consumer devices as a way to test the board. Mixed flowing gas or flowers of sulfur testing. These are testing for corrosive gases. And that is very common, say, in the server industry or areas, say, that you might have more corrosive gases as part of the environment. So not necessarily, say, in Boston, but if you are in India, where some of these server companies are, they're more worried about that particular type of environment. And those are extremely hard tests to pass. So you start having these different types of reliability testing, and it really comes down to the customer in terms of which one represents a use case for them. And then there's many years of background of, okay, if we do this thermal shock testing, it means this much of a thermal, or the lifetime based off of the thermal response. If you expose it to this much gas, that means that it has this amount of lifetime. And those have just become standard as part of the different companies' reliability requirements.
You talked about India, and I remember when LEDs, kind of the early days of LEDs, they used to use a silver backing on a component. And everything was well. The original promise of LEDs is they last forever. They never go out, which they've modified that since then. They're certainly better than incandescent light bulbs, for sure. But there was suddenly a lot of failures. And I guess looking back in retrospect, it was determined that the sulfur in the air in certain regions of the world, and this particular case study was India, caused tin whiskers or some form of corrosion and a failure of the product. And of course, we learned and we stopped using that material We didn't
Right.
we didn't stop putting sulfur in the air. We just stopped, using the materials that the sulfur created a reaction to. But I guess you kind of have to, in the conformal coating world, you have to kind of prepare for everything, right? Known and unknown, because it's a harsh, cruel world out there. And through IoT, electrification of cars, and just the advancement in electronics and automobiles in general, whether it's an internal combustion engine or an EV, there's more and more electronics going into these harsh environments, and wearables and other things. One of the challenges I see is there's a lot of consumer devices taking up the IoT space. It's not all high rel IPC class 3. It's a lot of class 1 and some 2. And the way our system of standards works, if it's class 1, it doesn't really have to be built as well as if it's class 3, right? From a solderability standpoint, allowable amounts of voiding, all sorts of things. And I think one of the really commonly identifiable symptoms of that is in public EV charging stations. Right now, there are tens of thousands of public EV. I'm not talking Tesla. They kind of do that better. But on the public station side, there was a very fast, rapid demand, sudden demand to build all these charging stations. And I don't know this for a fact, but I can hypothesize that a lot of companies jumped into that space that maybe really didn't understand harsh environments and things like that. And according to a government study, about 25%, at any given moment, about 25% of those public chargers are broken. And that is really impacting the EV adoption statistics. And it's slowing down. And that's because you can't find reliable chargers. Some areas just don't have any chargers, reliable or otherwise. And those areas that do have chargers, urban areas, things like that, like in California, 25% of them are broken. And, that's really an issue. And I believe, I think it's due to a number of reasons: vandalism, stupid people tricks, people hit them with cars, But I think the majority of the problems is they're not really built for the intended climactic operating environment they're used in. And they're not class 3 devices. No one dies if they don't work. But I think we almost need, from an IPC standpoint, we almost need a new standard. 1, 2, and 3 seem to work well, but we almost need like an H, harsh environment standard. So maybe we don't need the same solderability requirements of class 3, but we certainly need the same protection as class 3 might afford. And whether it's a class 1 product, whether it's a toy a kid takes into the backyard, or a connected snowmobile, some electronics on a snowmobile, that's certainly a harsh environment. And I think more and more of our electronics are going to need some form of better protection, whether that's in a case, weatherproof case, moisture-proof case, or on the surface of the board itself, as your company does. So I see the need for protection, whether it's conformal coating or otherwise, rising as components miniaturize, as boards become more dense, as electrochemical migration becomes more prevalent because of the reduced spaces between conductors, and this proliferation of these devices into harsh environments. I see nothing but increase in your part of the contribution to the assembly world.
I completely agree. And I think you really hit on something that is quite challenging for the conformal coating world, which is the idea of the miniaturization of components and more complex boards. Because the problem with this particular trend is that it becomes harder to mask. Mm-hmm. Have a smaller board with components that are closer together. You're, as you mentioned, electrical migration, you're going to have a lot more issues there if you don't protect them effectively. And masking becomes really difficult when things are miniaturized.
Right.
So this is where kind of innovative technologies and getting rid of masking is super important as the trend continues in that direction. And that's where I think Actnano found its niche very early on, was that because of our soft nature gel state and what we call deformable coating, we're able to basically forego masking in the majority of cases and also coat over connectors. Right? And that's actually pretty uncommon when it comes to, say, your traditional conformal coatings. So this is a big challenge for the industry, one that like we are poised and already tackling, but it's not a ubiquitous solution yet, I would say. So it is a very big problem, and I completely agree with you on the need to think about this trend and the reliability that's going to be required as we do electrify more of our world.
So as you're getting ready to help people as they electrify more and more of our world, do one more thing. Get out your crystal ball and tell me, where do you see the future of conformal coating materials going from a technology standpoint? We talked about from a practical, more and more people are going to have to conformal coat their boards or come up with some other form of protection. From a technical standpoint, where do you see conformal coating going in the years to come?
Yeah, so I think one trend we're already seeing, and this is something that IPC is in the process of trying to better qualify, is the fact that we're getting really unique types of chemistry. We're not in the same classes of chemistry. This is not unique to Actnano. This is just a general trend within the industry, is that people are bringing more complex chemistries to try and tackle some of these really difficult environments. And that's really exciting as a chemist to kind of see all of these new innovative chemistries and hybrid materials make its way into the marketplace, all of our Actnano materials included in that. But it's not us, it's everybody, right? That's thinking about new ways that we need new chemistries and to tackle it that way. But for me, where I wish we go as well is that more people think like Actnano, in the sense that you approach things from a safe perspective, right? New chemistries, everything are very interesting, but we don't want to get in a space where you create something that does more harm to the world. So innovating in a way that tackles sustainability topics while also thinking about the protection of devices as things change is an interesting and hard space to be, but one that I hope is a trend in the industry to move towards that.
Awesome. Well, I wish you and your company much success on moving toward that direction and continuing your move toward that direction. Not starting it, certainly continuing it. Thank you for sharing your thoughts and your wisdom and your expertise with me and my audience. I really appreciate you being on the show. Dr. Cassandra Zentner, thank you so much for being here today.
Thank you for having me. This was very fun.
I agree. I had a good time. And one thing I really love about hosting the show is I get to learn a little bit about a lot of different things. So if I could happen to randomly sit next to a conformal coating person on an airplane, I can at least hold a 1-hour conversation with them, right? Before I run out of knowledge. So that's come in handy throughout my career here. So thanks for enlightening me and educating me, and thanks for agreeing to be on the show. I really appreciate your time. Well, that's another episode. Thanks for listening to or watching the Reliability Matters podcast. Be sure to subscribe to the podcast on your favorite podcast app. Or if you're watching this on YouTube, be sure and click the like, subscribe, and bell icons to be notified when new episodes are released. We release new episodes on the second and fourth Tuesday of every month. A special thanks to Circuit Assembly Magazine's PCB Chat at pcbchat.com and Ascendo Reliability at reliability.fm for syndicating the show. Thanks again for being part of our podcast family. Stay safe, stay healthy, stay happy, and perhaps most importantly, keep doing it right. And I'll see you again in 2 weeks.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.